Welcome back to part 2 of section 5.4, basis and dimension. So we talked about, just as a quick review, how to take and find any vector and you express him as a linear combination of the basis vectors. That comes into play when we are taking and looking at like a vector 3, -1, 2. Literally, when we talk about 3, -1, 2, we actually used him with respect to the standard basis vectors. So he's 3 of the I vector minus 1 of the j vector plus 2 of the k vector. So these guys right here are his coordinates according to the basis that we started with. So to get this location, do 3 of the first thing minus 1 of the second thing plus 2 of the third thing. Okay, so we could write that, coming back up here, -136 is 71/56, 113/56, and -33/28, but with respect to the v prime basis, and I'll call that s prime, okay, or with respect to s. Okay, so we'll just call that s. So let's go ahead now and take and see if we can find the same location, but with respect to our v1, v2, v3 basis vectors instead of the ijk basis vectors. So what you're going to want to do is, again, set up, our linear system, c1, v1 plus c2, v2 plus c3, v3. But now we want to make the vector 3, -1, 2. And so we'll set up a system and find out what his coordinates are with respect to not ijk, but v1, v2, and 3 vectors. So go ahead and do that, and then we'll come back together and see what you got. So here's what I got using my vectors. We set up the linear system and RRAF. So 3, -1, 2 with respect to the ijk basis is the same as 356, -1156, 27/28 with respect to the v1, v2, v3 basis. Okay, so I hope that's made sense. And the next thing I want you to do is find another basis for R3 besides ijk or the v1, v2, v3 that we found before. So again, we'll have you pause and find that for us. And then we'll compare notes. So now that you've come up with yet another basis, what did you notice that they all have in common? Well, hopefully you'll notice that all 3 of the bases each had 3 vectors. Okay, and that important thing, the fact that each basis for R3 has 3 vectors, is what we call the dimension of R3. So the dimension is equal to the number of vectors in any basis for the space. Okay. Now, in 5.1, we expanded our view of vectors from arrows to anything that satisfies the 10 axioms. And in particular, we saw that we had P sub n, which was polynomials of degree at most n. Polynomials of degree at most n. Okay, and we had capital M of m subscripts little m and little n. These are matrices, or m by n matrices with real coefficients. Okay, and unless I tell you otherwise, we're going to use standard operations. So let's go ahead and examine P2 with standard operations. So what would be the standard basis for P2? Well, we actually saw this guy at the end of last activity, x squared, x, and 1. Okay, because we could write any vector we want out there, u equals ax squared plus bx plus c, as a times the x squared vector plus b times the x vector plus c times the 1 vector. And how is this related to the standard basis for R3? Well, we gave you that hint last time. X squared is like 1x squared plus 0x plus 0. So it's equivalent to the arrow vector 1, 0, 0. Similarly, x is equivalent to the vector 0, 1, 0, and 1 is 0, 0, 1. Okay. And we notice that these guys are the I, j, and k vectors, respectively. Now, what I want you to do is create a basis other than the standard basis for P2. And then I want you to express this u vector, 3x squared minus x plus 2, as a linear combination of those basis vectors that you made here. So again, we'll pause while you work on that. Okay, so I happen to choose a nice basis, 2x squared minus 4x plus 5, and 4x plus 1, and 3x squared plus 2. Why is that nice? Well, to help make a point, those are equivalent to these vectors back in R3. So even though they're polynomials, they behave just like the arrow vectors did in R3. And solving that, we can see that we will still get the exact same coefficients that we got. And so this u vector, 3x squared minus x plus 2, which coincidentally happen to be the same coefficients, 3, -1, and 2. So I'm hoping to drive home the point that these guys, even though they're polynomials, they behave just like vectors do. So they're a vector space. And hopefully, if you think about this a little bit, any basis for P2, notice that we have 1, 2, 3 vectors, and up here we had 1, 2, 3 vectors. So any basis for P2 will have 3 vectors. Okay, so that tells me that the dimension of P2, polynomials of degree 2, at most 2 I should say, is 3 because it takes 3 vectors to cover the entire space, no more, no less. Okay. Now let's look at M22, matrices that are 2 by 2 with standard operations. The standard basis for this vector space would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. So you should hopefully notice that there were 4 of these guys. So the dimension of M22 is going to be 4 because it takes 4 vectors to cover the entire space of 2 by 2 matrices A, B, C, D. Okay. And how is this related to Rn? Well, think about it for a second. Let me have you pause, and then we'll get down to this guy right here and end our video and pick up on the next. All right, so hopefully you noticed that the matrix 1, 0, 0, 0 looks and acts just like the vector, the elementary vector 1, 0, 0, 0. And similarly, we've got our other elementary vectors here in R4. And I made up a non-standard basis for M22. So here are my guys, and we'll pick up there in the next video.